Should I begin?
Yeah, I think so. It's just three of us right now.
No.
Okay, so today is a very happy day for Suhas, and actually, it's huh?
That comes later.
No, actually, it's my birthday.
Oh,
I mean, happy
I
anyway.
didn't know that. Happy
It used to
birthday.
be much happier when I was younger. Now I sort of feel that every year I'm getting older. Anyway, so he's done some interesting work, and he's going to tell us about coalition formation and cooperative networking.
Okay, hi everyone. Good morning, and welcome to my master's thesis defense. My thesis is titled Coalitional Games in Cooperative Networks. Let me begin by describing the context of our problem and by motivating it by throwing some questions. The term cooperative communications has been the subject of a lot of research lately in the communications community, and it means different things to different people. It's been used in a very wide variety of ways. It's been applied to sensor networks, ad hoc networks, and even cellular networks. And we're all familiar with cooperative communications in one form or the other. Another upcoming technology, cognitive radio, which is another term which is used very broadly these days, is likely to enable cooperative communications or to help enable cooperative communications in some way in the near future, we hope. The question we pose in this thesis is, when users in general are made to cooperate or allowed to cooperate, does it always result in gains for each cooperating user? In other words, does each user stand to gain, or will users sometimes have incentives to break away from a cooperation scheme? Right. Another related question is, does cooperation buy efficiency for the system overall? Meaning, is there some value in having all the users cooperate? If so, is this always possible? Can we always guarantee it? If, assuming that the users in question are rational users, they're able to make their own decisions. Or again, will they have incentives to break away, either by themselves alone or in groups? And we'll see in a minute what we mean by this in mathematical detail. Can cooperative protocols induce the formation of disjoint groups of users that are stable? And stable, that I've underlined, I'll explain in a minute what I mean by it formally. But just to give you an idea, stable here means that everybody is happy with their cooperation scheme. They don't want to leave. They don't want to defect. So let me begin with a very simple toy example. In this example, there are three users, three transmitters, A, B, and C, communicating with their respective receivers, which for this example, for simplicity, we assume that the receivers are co-located. So they're co-located. And these receivers are allowed to cooperate by jointly decoding their received signals. So one can think of various ways in which these links can cooperate. So if the receivers of A and B decided to cooperate, they would jointly process their received signals, and then A and B would receive gains from that. C may be left out of the cooperation scheme, or B and C may cooperate and A may be left out, or several other ways, or A, B, and C together may cooperate, or none of them may cooperate. And we also assume here, for the purpose of this toy example, that whenever users cooperate, the sum rate achieved from joint decoding is split equally between the members in the cooperating coalition. So the question posed here is, what cooperative behavior emerges from this simple example? That is, what coalitions are formed? And here I've drawn a picture of what really happens. So what I've done here is I fixed the channel between transmitter C and the receiver, and I've varied the received SNRs of A and B, meaning I've just moved them around. I'm using a path loss model. And we see that it's very apparent immediately that the grand coalition, which is a coalition of all three users, is not always the stable coalition. This blue region here represents the grand coalition, which I represent by this notation A, B, C within parentheses. And you'll find that at some other tuples of received SNR, the grand coalition is not stable. For example, in this region, B, C decide to break away from the grand coalition and form their own coalition, and they leave out A from the cooperating scheme because they don't stand to gain from it. So in general, it can be said that grand coalition is not always stable. The grand coalition is therefore not the obvious solution, and in general, it depends upon the the apportioning scheme that we utilize.
Really clear. In like one of these regions,
Yes.
right, like say the yellow region,
Okay.
right? Somehow you concluded that the policy where B and C work together and A works by himself has some kind of a property. So what is that property?
In this simple example, that property is simply preference relations. So you could think of it this way: each user makes a list of the coalitions that he would like to be part of, and he arranges them in a priority order.
Yeah, but he's saying what is the quantity that he's?
So the metric that we are using is sum rate. The sum rate is being apportioned. So when B and C cooperate, their receivers are jointly decoding the received signals, and they have a certain sum rate. And I said earlier that they split the sum rate equally within any given coalition. So B and C will equally split the sum rate that their receivers see. Just as in this grand coalition, they would split it 3 ways equally. So it turns out that in this region of SNR A and SNR B, B and C don't want to be part of the grand coalition. They separate out, and they get better performance, better rates than they would get over here, than they would get if they were part of the grand coalition.
What's going on with the receivers? You had 3 receivers on the previous picture.
Okay.
Right?
So I assume that the receivers are co-located for simplicity, and when any 2 users cooperate, or if 3 users cooperate, the receivers confer among themselves and they jointly decode the received signals. And I'm assuming ideal decoding here. So when the receivers jointly decode, they achieve a certain sum rate, and the sum rate can be apportioned between the cooperating members of the coalition in any manner.
So, another simple question. Why would the receivers not always cooperate with each other?
That's
The
okay.
receivers
Yeah.
aren't, the receivers are the base station, right?
Yeah.
It's the users of the PC, they have to decide whether they want to
Okay. So in this
exchange, digital coins and cooperate and all that sort of stuff.
right. So for the purpose of this simple example, I've made the users as the receiver. Okay. There's no cooperation between the transmitters here. Okay. The users are the receivers. You can think of it that way, and they get to decide who cooperates and who doesn't cooperate. So I've chosen this very simple. This is just to motivate sort of the whole idea. For this simple example, the receiver is just splitting the sum rate equally. Maybe there would be some way in which they don't split the rate equally, and it turns out that the grand coalition is always stable. For this simple example, the answer to your question is, why do they not always cooperate? Because sometimes users have incentive to defect. But I am assuming that users are the receivers.
Right. That's different from what you had up written down, but now I understand.
So am I to conclude in the yellow area that in this configuration, there's no incentive to defect by anyone?
Exactly.
Is it also true that the rates people get are at least as good as for any other configuration?
So
Like in the yellow area?
in the yellow area, so what I plotted here is the stable coalition structure. And by coalition structure, I mean simply a partition of the set. The set is A, B, C. And here's the coalition structure B, C together, and A alone. And it's stable. When I say it's stable, I mean no user has incentive to defect either alone or as a subgroup. So I could say that the rate that C is getting here, he's happy with it. He will not defect alone, or C and A will not pair up and move away and begin to cooperate.
So is that what you were saying? Is that saying that if C went over to the right to the A, B, C one,
Yeah.
that he would actually get less rate by
So
moving over?
So here okay, let me clarify. I've fixed the received SNR of C to 20 dB, and I'm moving A and B around. Right. So if you were to move from, logically, if you were to move from a point on this plot to, say, a point here, then what has happened is I've increased the received SNR of B while keeping, say, if I move along a horizontal line, I've kept the received SNR of A constant. I've increased the received SNR of B, and C is fixed anyway. So instead of BC being the stable, BC, A being the stable coalition structure, it's now everyone by himself. It just turns out to be that way.
So why aren't there SNRs where there are no stable structures? Like, is it that just for this example,
Yeah.
because that
Yeah.
structure
That's
Yeah.
that's part of the thesis too. You can
That's-
tell when stable structures are there. And
That's
when they're
yeah. So I'll come to that in detail.
But here you had just like a set of fixed set of strategies, right? So each can
Yes.
have some value just like.
Yes, I'll come to that
I'll
in
just
detail.
say,
Yeah.
How are you computing the rate, say B comma C
Yeah.
and A, right?
Yeah. So I'm assuming here that they're using Gaussian signaling. I'm doing ideal decoding. So BC are being the receiver BC is being treated as a receiver, one receiver with two antennas, and I'm treating A as Gaussian interference. Yeah. Very simple. And when all three are cooperating, it's just an extension to three users. Right. So the whole idea of giving this toy example was to just show that the grand coalition is not the obvious solution. The grand coalition, again, just being the coalition of all the users together. So here's an outline of our work. What we've done is we've studied user cooperation under the framework of coalitional game theory, and I'll explain why coalitional game theory fits in so well. And in particular, we've studied receiver cooperation in an interference channel, transmitter cooperation, and receiver cooperation. So here the focus is on the transmitters cooperating, and finally receiver cooperation through multi-user detection in a multiple access channel. All right, so let me come to the details of the coalitional game theory. I'll just give a brief overview just to familiarize you with the terms and the things I'll use in this presentation. So formally, a coalitional game with transferable utility, and I'll explain what transferable utility is. A coalitional game is represented as a tuple S comma V, and is defined through a finite set of players S and a value function V which maps any given subset G of S to a real number. So this V is termed as the value function, and essentially what it does is takes every possible subset of S and assigns a real number to it, and that is the value of that subset. It's the worth of that coalition. It's actually what that coalition can achieve if that was the coalition cooperating without everybody else. The payoff is just a term we use to describe the share of the value V of G to each player in the coalition G. A characteristic function form game is one in which V of G is unaffected by the strategy of members who are not included in the coalition G. So going in the toy example, suppose there were 4 players, A, B, C, D, and AB formed a coalition. The value of AB would not be affected by the strategy of players C, D. That would be a characteristic function form game. And coming back to transferable utility, when V of G can be flexibly apportioned between cooperating players, then the game is said to have transferable utility.
So there's this flexibly apportioned seems like those are imprecise words.
Okay, flexibly apportioned means
so whatever the sum is, you can divide it
in any way you want. Yeah, it's
So it
fluid.
seems-
It's like water. Yeah.
It seems like some examples, right, have some amount of flexible apportioning, but not completely flexible apportioning. Like a kind of a MAC channel, right, might have a sum rate bound and then two individual bounds, right?
You're right,
that
yeah.
Says, so is that, can you go back a slide?
Yeah. Okay.
So is that transferable or is that
That's
not
okay.
transferable if you can only
That's a good question. So what I think, let me draw a picture. What Roy is saying is, if I have a MAC channel and I have something like that, and so if I were to operate somewhere here, I could move anywhere between here, but I can't go beyond this.
Right.
So that's what he's saying. So that's a question: do we treat it as transferable utility or not? That's a question of how you model the game, and in fact, I'll be coming to that. And we've treated the game as transferable utility within those bounds. So within those corner points, it can be apportioned flexibly. So I've treated it as transferable utility. For other examples, we'll see that for not that shape. Well, for another example, we'll see that we also deal with non-transferable utility games.
So when you say characteristic function form game, is it you're assuming that games are such that users outside a coalition will not affect you?
Yes.
You're considering only those value functions.
Yes.
He's saying this is what is called as a characteristic function form game. Then in his thesis, as he goes on, you'll see there are some situations some types of cooperation are not characteristic.
Also, a priori not assuming whether outside group members affect you or not.
Oh, we're not assuming that. I'm
Like
just
that, then
defining
you
what characteristic function form game is.
If it turns out that the value function is such, then you call it a characteristic.
Yes, I was just defining it. All right. So, moving on, a coalitional game with transferable utility is said to be cohesive if it has this following property. Meaning, if I take the set S and I make an arbitrary partition out of it into the subsets S1 to Sk, where K is arbitrary, then the sum of the values of each of these subsets treated as coalitions is less than or equal to the value of the grand coalition. If it has this property for any partitioning, any arbitrary partitioning, then the game is said to be cohesive. And another related property is superadditivity. A game is said to be superadditive if for any two disjoint coalitions G1 and G2, the value of the combined coalition G1 union G2 is greater than or equal to the sum of the individual values. And in fact, superadditivity is a stronger property than cohesiveness. Cohesiveness follows from superadditivity, but not the other way around. And here I have a very simple example to sort of illustrate superadditivity as well as transferable utility. Sorry?
I mean, it seems the other way.
Superadditivity implies cohesiveness. Is that what I said? Because here I've just taken any two G1, G2. I didn't say that G1, G2 is a partition.
Okay.
So if you have, here I have to consider the entire set. I have to make a partition out of it. So superadditivity will imply cohesiveness, but cohesiveness does not necessarily imply superadditivity. Okay, here I have a simple example. So let's see. There's a group of two people which I call a coalition G1, and the value of G1 is 4, and there's another coalition G2. The value of G2 is 2, and in this simple example, they're just sharing the values of their coalition equally. So each of these men has a value of 2, and each of these men has a value of 1 each. Now, suppose if I were to combine these coalitions, I was to fuse them together, then and if I had the property of superadditivity, then I know that the value of the combined coalition would be greater than 4 plus 2, 6. So I take V of G1 union G2 to be 7. Anything greater than 6 is fine. So just to illustrate what transferable utility can do, in the top box here, I assume the same equal splitting strategy is being employed. That is, everybody gets an equal share of the value 7. Everybody gets 1.75. And you can immediately see that the people who had 2 earlier on are not happy anymore because they're now getting 1.75. So if this equal splitting strategy were to be enforced, then this path is not favorable for the men in purple and the man in purple and the man in red. If on the other hand, if I was allowed to have transferable utility, then I can always find an apportioning scheme such that everybody is happy, because I can give each one of them what they had earlier, and the additional benefit I got from fusing the two coalitions together can be distributed in some way. So here I have 2.25 and 2.25 to the purple and the red, 1.25, 1.25 to the other two guys, and everybody's happy. Here, of course, I haven't shown the other details of this. I haven't shown what would happen if red and green were to form a coalition. Maybe they can do better. But just to give you an idea what transferable utility can do. All right, and coming to the most important concept in coalitional game theory, the core. So this slide is about the core, and I'll sort of build up to it, what exactly it means. So a G feasible payoff vector is simply a vector containing the payoffs of all the players in any coalition G, such that the sum of their payoffs equals V of G. That's straightforward. And a continuation of that, an S feasible payoff vector, where S is the universal set. An S feasible payoff vector is simply called a feasible payoff profile. The core is simply the set of all stable coalitions, basically. So stability is defined here through what payoff each player receives. Right? Formally defining core, the core C of V of a game S comma V for all G feasible payoff vectors is the set XS, where I use this notation here, XS, such that there does not exist any subset G of S such that the payoffs in G are component-wise greater than the payoffs that each of the players were receiving in the grand coalition. That's a mouthful. Let me say that again. So basically, the core is the set of all feasible payoff profiles, all the payoff vectors to the grand coalition, such that no subset G can deviate from it and achieve a sum rate greater than the sum rates that they were getting in the grand coalition.
There are no sum rates here.
Oh, sorry. So I'm sorry. Yeah. So let me say that again. So a core is basically the set of all payoff vectors, such that no coalition G has incentive to break away in that element by element or component by component. Every player in G gets a higher payoff than what he was getting in the grand coalition. That's what I mean by ym greater than xm.
Shouldn't you have, the general concept of stability for any partitioning of users, and then a core is a special case of that?
I'm sorry?
I would assume that you will say this about any partitioning of users. That in any partitioning of users, there is no other partitioning, like no user can deviate. Some definition like that, and then core. I'm just asking, is there a definition like that? Core is a special case, right? Like where you are comparing the grand coalition with other coalitions, right?
No, the core is basically the set of all, not just for any partition, for the grand coalition.
Yeah, for the grand coalition, all the feasible vectors that.
Okay, I see what you're saying. Okay, so you're saying that there are other coalition structures, other partitions which can also be stable, such that no subset has.
Yeah, I'm saying that the definition.
In general, that's true. But we'll see why in the purview.
Specific definition for core. Why not?
It is why is it specific to the grand coalition? You're saying.
Yeah.
So this definition is actually not specific to the grand coalition. I'm sorry if I insinuated that. So this, if you'll see that G, subset of just 1 comma m, you could have a certain partition which is stable, and what this definition of core is saying that no subset of users in general, no subset of this set 1 comma m can deviate from that existing partition, such that each user that deviates gets a better payoff than what he was getting in the earlier coalition structure. True. However,
Right? If you start with a definition is usually a self-contained object, right? And so somehow maybe it is all right. Like what are the x's?
okay,
This definition is out of the
But these 1 to
It's
m.
just a mathematical version of
just a standard.
the x's are just payoff vectors. Sorry,
1 to m, the set is a set of all players S.
the set of all players. Yeah.
That's
Yes.
S.
Yeah. It's S, but that doesn't mean you treat it as a grand coalition.
No. So core is just a notion of stable coalition.
No, I understand. I'm just saying why introduce 1 to m. It's just you're saying any subset.
Any subset of
To bring in
S.
grand coalition to talk about core, right?
Sure.
But the thing is, the moment you have those two properties,
So I'm just coming to that.
Later, yeah.
Okay.
You have to make some assumption that the payoffs are non-negative. Like you enforce this feasible payoff vector being something, but like the linear sum adds up to a number, right? But
Yeah.
like can you
Actually, yes, I do.
create games where some people choose a negative payoff to give other people
No.
very high positive payoffs?
No.
I mean, all your games all are great games.
So the answer to that question
That's
is
a good question, but I don't think I've ever seen it.
the answer to that question is so I have a V of G for every possible G, right? And this G can be a singleton. So I have a V of I, and that is some value. This is the value of I when I acts alone, not cooperating with anybody. So V of I is likely to be some positive number. And therefore, what you're saying, if I was part of a coalition G, he would not accept some negative value for himself because he can do better by acting himself. So he would break away.
Essentially, are you assuming that the payoffs are non-negative?
Yes, I am.
So the flexibility,
I'm assuming all the VGs are all non-negative. I should say that.
But in economics, they do give negatives to some, like
It's all relative anyway. I just push the least V of I to
Yeah,
positive.
but I think coalitional games, when they sort of talk about this, the payoffs are always non-negative.
Actually, it doesn't really matter. If I have VIs,
I've not seen it.
I can just push everything by a constant up.
Well, you mean a coalition? It's just a
I mean, you need super, so that
Coalition
if
structure
you
is a
have
partition.
negative things, maybe if you have super additivity,
Yeah.
still it's okay. as well.
Coalition is a group though.
Coalition is a
As long
group.
as you have that
Yes.
property.
The negative positive comes in the flexibility issue. I mean, when you are
No,
talking
that's
about
what, right?
flexibility.
No, as long as you have super additivity and cohesiveness, right, you can still talk about it with negative payoffs, then I think everything holds.
You can talk about it with negative payoffs. If you have a negative v of I, say v of a player, v of 3 is negative 5. He can break away and get negative 5. If he was getting negative 10 earlier, he'll always break away and get negative 5. So I'm not sure if the question of shifting the entire, I don't think it's very, it doesn't make a difference, I think. So moving on, under the conditions of super additivity and transferable utility that I just described, the definition of the core can be actually simplified. So instead of talking about component by component doing better, I can just talk about sum rates. And now I can define the core C of V to be all the payoff vectors xs, such that the sum, such that there does not exist any g for which the V of g is greater. In other words, that the sum of the payoffs that they're getting in the grand coalition is greater than equal to what they would get if they broke away, which is V of g. And if this was true for every possible subset g, then no subset would have incentive to deviate or to break away. And then you can say that there exists at least one distribution of payoffs in which the grand coalition is stable. In fact, when we have super additivity, the only candidate for the core is the grand coalition, because the sum of the rates is maximized, the sum of the payoffs is maximized by the grand coalition. Transferable utility simply allows me to talk about the core in terms of sum rates rather than component by component. However, it is important to point out at this stage that the core can actually be empty sometimes. It's not guaranteed to have at least one feasible payoff profile. And when the core is empty, it means that there is no stable form of cooperation. Let me illustrate that with an example. So in this example, I have 3 players, 1, 2, and 3. That's the set S. V of S, which is the value of the grand coalition, is unity. V of I, for any I, 1, 2, or 3, I set to 0. And V of G, for any coalition G of cardinality 2, I set to alpha, where alpha is a number between 0 and 1. So I've described the entire game here. Yes, sure.
For example, when you consider V of I,
Yeah.
do you also consider the cases in which one player is left out as a single and the other two gets together? Does it make a difference if the other two gets together or not?
So that's what characteristic function form means.
So we still assume that this is characteristic function.
Yes, I'm assuming this is characteristic. I should have said that. This is a characteristic function form game, right? I don't. So actually, whenever I have V, and I'm associating any set G with a number V of G, then I'm assuming implicit.
If you don't have characteristic function form, you can't even define a value.
You can't, yeah.
Because if the value becomes sort of what is it?
The value will depend upon.
Become like a bell number.
Yeah.
Yeah.
Well, not exactly, but the value will then depend upon what the other people are doing. So you can't define one number.
Okay.
Right?
Okay.
So implicit in this definition of the game is the fact that you're right. It's a characteristic function form game, right? So to ask the question of whether or not there exists a core is to ask whether all these inequalities can be satisfied. And let me explain what all these things are. By these R's, I denote the payoff of each user subscripted with the index beside it. So for there to be a non-empty core, I must have a payoff to user 1 which is greater than its own value, which in this case is just 0. So I need R1 greater than 0. Same thing for R2, R2 greater than 0, R3 greater than equal to 0. Then for the coalitions that have 2 members in them, their sum payoffs should be greater than what they can achieve as a group. So R1 plus R2 should be greater than equal to V of 1, 2, which is alpha by this definition. And the same thing for the coalition 2, 3, the same thing for the coalition 3, 1. They're all alpha. All their values are alpha. And finally, I have an inequality constraint which says that R1 plus R2 plus R3 should be equal to V of S, because they should use up all the resource available, which is equal to 1. Right. So we see that the existence of a non-empty core is basically equivalent to checking whether a linear program is feasible or not. Where this is the linear program corresponding to this coalitional game problem. Right? And it's easy to see here that this game is super additive. You can list out all the possible combinations, v of 1 plus v of 2, 3, v of 2 plus v of 1, 3, and so on. You'll find that always the value of the fused coalition is greater than or equal to the value of the sum of their values. However, it's easy to see that if I add these three inequalities and compare it with this equality, I'll find that the game has a non-empty core. That is, this linear program will be feasible only if alpha is less than or equal to 2 over 3. Right? If I add these three, I'll have on the left hand side 2 times r1 plus r2 plus r3, and on the right hand side I'll have 3 alpha. And comparing it with this will give me this condition. So in general, it's not true that the core must always be non-empty. It may or may not be, even when I have superadditivity. Okay, with that background, let me move to the first line of our work, which is receiver cooperation through ideal joint decoding.
So when you said adding R1, R2, R2, R3,
Yeah.
Superadditivity is defined for disjoint sets. I mean, because
Yes.
you can't add those three. You can't have two coalitions the same.
Sorry, can you say that again?
Can you add R1, R2, and R2, R3 and compare it with R1?
Oh, here I'm not invoking superadditivity here. I'm just adding these three inequalities to compare it with this equality, and then I'll get this constraint that alpha, if all these were feasible, then alpha will have to be less than or equal to 2 over 3. Yeah. But you can see just by this game definition here that the game is superadditive. All right. So, any other questions? We study receiver cooperation in the context of an interference channel, and our basic motivation for studying this problem is as follows. When different types of devices or different types of networks coexist and have different types of links sharing spectrum, then transmitter cooperation may not always be possible, because transmitters may be operating on different protocols. They may not be aware of each other's existence, and they may not be able to talk to each other to cooperate. So in such a situation, receiver cooperation may be the only feasible way to enable cooperation. And in this context, a spectrum server is something that can enable us to achieve this kind of cooperation. A spectrum server is simply a central entity to which these receivers can relay their signals. And in our case, it can help the receivers to jointly decode their received signals. Okay. So, and in fact, these links don't have to be wireless links. In the abundance of fiber, they could be wired links or fiber links. And
the 40-second new definition of a
Spectrum server,
Yeah.
I really like this one actually.
So I don't think anyone else is using this spectrum server, right? The joint decoder spectrum server.
well,
So when
I
I put
think
this up,
if-
people said, "Oh, this really makes a lot of, if you say that you have fiber everywhere,
Yeah.
and then so why not talk about receiver cooperation? In fact, we have this project, Gaspar and Radio at Cornell, what's her name?
Cadrio.
Right. So they all have a joint. They got a new Nets grant funded to do receiver cooperation.
So it's the opposite of. Did you realize you and Jerry were doing a spectrum server, which was a transmitter
Yeah,
side?
that's what they were doing. They were doing that. Base station cooperation. Yeah.
Okay.
so we could think of such a spectrum server or some entity there, some central entity, which allows these receivers to relay their signals to it and jointly decode their received signals and thus enable cooperation.
I guess I'm just laughing because, like, I guess Chen, who uses that word, it has like the same picture, these are totally different.
Yeah.
And Omer has some picture
Right.
also uses
Yeah.
totally
Sure.
different. All right.
All right. So, setting up our model formally in the context of our problem, we model this problem as an interference channel with additive white Gaussian noise and flat fading. S again is the set of links, the set of players which are now links. The ith link input outputs are the xi and the yi. The yi is related to the x's in the following fashion, with fading gains being multiplied by the x's, and Zi, which is the complex noise variable being added. And we have a power constraint at each transmitter of this form. And we assume that transmitters of each link use Gaussian codebooks. So what does it mean for receivers to cooperate in this context? Receivers in a coalition can jointly decode their received signals, and whenever two receivers jointly decode their received signals, there is immediately a gain from cooperation. So what happens is this type of cooperation turns the interference channel into what is called a CMO MAC, or a single input, multiple output, multiple access channel, where the single input refers to the fact that each of the transmitters just has one antenna. Multiple output refers to the fact that whenever two or more receivers are cooperating, they can be sort of treated as a single receiver with multiple antennas. And multiple access channel simply refers to the fact that there are multiple transmitters, multiple links competing for the same resource. Signals from links not in the coalition are treated as interference by any coalition. We model this problem as a coalitional game with transferable utility. So this comes to your question earlier. When I have a MAC and I have sort of a pentagon kind of shape, and I'm operating at some point on the sum rate line, can I model it as transferable utility? The answer is yes, you can, as long as you stay within those corner points. So we model it as a game with transferable utility, and when we say transferable utility, we mean again that the receivers in a coalition can share the sum rate flexibly. The question now is, what are the optimal and stable coalition structures? So optimal here.
You're being sort of vague here, right? Like you say, as long as we stay sort of in that constraint set. But what does that mean? Like suppose you say, oh, the way the game works is they have to share the rate equally, right?
No.
But
What is it?
Well, I'm just saying. I mean, he has some examples.
Some examples, yeah.
The rest of it, now they're nothing equal anymore.
No, so that was when you had
That was just to
non-transferable.
motivate that example. Which
So-
the grand coalition is not always the obvious solution. That's all it is. From now on, it's.
So the short answer to your question is that yes, it can be modeled as transferable utility.
It can be what?
It can be modeled as a transferable utility game.
Using the word, are you sliding in a more or less in there? Just
No. It can be. No more or less. It can be.
all right. Well, we'll revisit that because I have an
Okay.
example in my head. I'm trying to.
Okay. So setting this up formally, a coalition of links in G, which is a subset of S, forms a Gaussian CMO MAC of mod G transmitters and a mod G antenna receiver. RG is simply a vector of rates for links in the coalition G. The value VG of a coalition is basically the maximum sum rate achieved by links in the coalition G, which we write as the maximum mutual information between XG, which is now a vector, and YG.
Can we go back to the picture again, just so I understand now everything that.
This one?
So in this picture, yes.
Yeah.
You're by default giving yourself the same amount of receivers as you have transmitters, or at least that's what you just showed.
Yes, there are links. Yeah.
Now,
You start with an interference channel,
right.
which means there's every transmitter has its own receiver. And then he's saying he's going to throw this spectrum server, right, which is being used or misused in so many different ways.
Okay, so
That's all it is.
so the definition of an interference channel then is that
One transmitter,
one receiver. But does it mean that transmitter 1 is also seen by receiver 2?
Yes.
Yeah, that's what interference channel is.
All right.
Yeah.
Do you have a picture without the spectrum server? You go a couple of back. That's actually the
Yes.
this is what is called an interference channel, right? And if you label, it's like there's one transmitter and there's a receiver for it.
So M pairs of transmitters. Nobody's aware of the
And
other.
usually in information theory, people work with just two. That's basically the interference channel that they can all do. None of them can do. Okay. All right. I was just trying to.
All right, go for it.
So, and in this case, because we put this thing in, we can do any number m because it becomes a CMO MAC. So we're not constrained to 2 anymore.
So now, somewhere implicitly in here is an assumption that those receivers aren't necessarily required to
Right. You're right. They're rational receivers which may choose or which may choose not to cooperate.
The server's not God, right? He's not telling them you follow my rules and
Right.
give me all your data or else. Nothing like that.
No, nothing like that.
So in that sense, it's not a.
So all these cooperation schemes that we're discussing, we're assuming that the devices or the intelligence that is implementing this cooperation is rational and has that much intelligence to decide whether or not it wants to cooperate.
It's not the spectrum server. The spectrum server is a slave that just does the decoding when you ask it.
So receiver 1 tells the spectrum server, I want to cooperate. Here's my token, or here's my signal. Can you please jointly decode it with the other two?
So in your previous slide, you said everything has fading channels. Could you tell us what you assumed about the fading channel? Like there is channel state at the receiver or at the transmitter or both or neither, or are you going to average, you're going to use code words that...
So I haven't explicitly considered channel state information at the transmitter because I'm not considering transmitter cooperation so far. In the next line of work, I will consider that, and there I have considered channel state information. Yeah.
Consider the transmitter cooperation.
Sure.
Like you define all these mutual information, but it's not clear what they mean, right? Without saying something about like you have some fading channel state.
So our model is very simple. We assume it's not.
Right? I think the assumption here is CSIR. So all receivers have perfect channel state information. I think that's not in my slides, so it's not here. And so if you go back a few slides later,
like getting an exam, you know. So you're saying, you think it's that there's CSIR but not CSIR.
So actually, for this simple example, I think we've assumed both GSIR and CSID.
And somehow, are you assuming you're calculating some kind of an ergodic capacity?
No. So I'm not averaging over the edge.
I think you are averaging.
Can you write the go on? You'll
Okay.
go on.
So
singleton, which is not cooperating with anybody, right?
yeah.
For that link, do you assume CS as a transmitter also? His own channel gain as a transmitter?
Yeah. I'm not sure. So the way I've defined value is So I've defined value of a coalition G to be the maximum mutual information between XG and the set of receivers YG, the receive signal YG, and the maximization over here is over XG. So yes, there is channel state information known at the transmitters.
So maximization is over. When you write T XG, what do you mean?
The distribution of XG, the distribution of X1, X2, X3 till X1.
So are you choosing distributions and then generating code books?
Actually, we have just assumed that we use a Gaussian code books.
Okay. And then you're signaling through some fading channel.
Yes.
Right. And so
Okay.
what's the relationship between the length of your code book vectors and like you see a new distribution of the channel state at every channel use? A new value of the channel state?
A new value of the channel state at each channel use.
Yeah. Is it a slow fading channel?
Yeah, it's a
or-
slow fading channel.
It may or may not be, but I guess the thing is I'll take it that I think I can make sense of this if you just fix the H's, but I'm not sure it's not clear to me that what and what you say, what you're gonna do might make sense, right, under some assumptions, right? But like I would have thought looking at this that you were gonna tell me, it's actually fast fading.
No,
Right.
I don't think.
no, he's right. He's right, and there's also that expression is somewhat wrong. Should be a conditioning on the channel state of the G at the receiver's.
Well, since he
Well-
doesn't have any conditioning, right?
Yeah, but it's wrong. I mean, we are assuming that. We are,
Well-
and you're
Yeah, I
right.
was
This is
thinking
ergodic.
I was thinking it was just some given a channel gain, you just basically signaling.
Okay.
Right now, whether you can argue whether it's slow or fast, it doesn't matter.
Say it again.
I'm saying given a channel gain, you basically do Gaussian signaling, assuming that you know that particular channel gain, whatever HK. That's all it is.
Actually, I don't model the fading
In fact,
explicitly. I'm just using it as a channel gain.
I think that term is
Yeah,
wrong.
this whole analysis is
That
not
that
fair.
term that you said it's a fading coefficient is just some. I just call it path loss. That's
So
what
I
used
just
to call it.
assume that basically it's a constant
Given
path
the
loss
path loss.
coefficient
Sort of,
between the transmitter and the receiver, and the way I thought of it was during this entire operation of whatever the game they're playing, it just remains constant. So I thought it's really slow,
It's just
or
a
it's
path
just a
loss.
constant.
I sort of see
Yeah,
it more
yeah,
as a path
that's
loss
fine.
than anything
That's what I
else.
meant.
So for that model,
In fact,
it's-
I always it always annoys me when she's the one she uses it for fading gain. That's why I think it's put it on there.
Yeah,
Like she says, then she'll say, oh, it's like fading, and then
Slow
she'll say it's a
fading.
non-fading ergodic phase, blah blah blah. I'm just saying, just call it a path loss. It's essentially a path loss, and when you have a bit of noise and
Alright.
interference that is being modeled as Gaussian, then you're just going Gaussian signaling. It's
Right.
just simple. And all the CMO math results basically follow because of that. The moment you say fading, what Roy is asking, right, you're sort of going down a very tricky slope.
Tricky
You have to really
path.
understand how he would do it.
Yeah, we haven't really modeled the fading. Yeah,
So-
just assume it's constant.
all right.
I guess that's why we didn't need to take the ergodic.
Yeah, that's fine, but I'm just saying that's some information.
Okay.
So here, so G, the capacity.
Yeah.
There are some questions here. So RG is going to be defined, R under bar.
Yeah.
All right.
This one.
No. Okay, that's the vector. All right, I see it. It's a vector. Now, it's for all. It's G exclude. All right, so it's X sub G exclude A for all A subsets of G, right?
Here.
Yeah.
Yes.
So
Yes.
subsets.
For all subsets of G, where G itself is a subset.
That's just typo. But all right.
Oh, this should be subset. You mean? Yeah. That's a typo.
Oh, sorry.
You're right. Actually, that's a typo. Okay. Yeah, I rewrote it in LaTeX.
No, my last final says I guess I
Okay. So, having defined the value of a coalition V of G, CG is simply the capacity region of a mod G link Gaussian CMO MAC, where G is just a subset of the set S. And we define the dominant phase of the capacity region CG, where the dominant phase is given by this relation, where the sum rate is equal to the value of the coalition G, and we denote the dominant phase by just capital D of CG, just some notation that we'll be using later. So from this, the results we have is that the game is super additive, which is a good thing because it means that the grand coalition maximizes the sum rate, and since it also has transferable utility, it yields us these two results. First, the grand coalition, that is the coalition of all links, maximizes spectrum utilization for the receiver cooperation interference channel coalition game, and that is because since it's a super additive game, the sum rate is maximized by the grand coalition, like I said, and since the sum rate of all the links operating on a common channel is maximized by the grand coalition, we say that the spectrum utilization of that common block of spectrum is maximized by the grand coalition. Second, the core of the receiver cooperation interference channel coalitional game is non-empty. In fact, we show that every point on the dominant phase D of CS of the capacity region CS of the grand coalition belongs to the core. So not only is the core guaranteed to be non-empty, it's also non-unique in that there's a multitude of points lying in the core. And a natural question that follows from there is there some way of picking one point out of these multitude of points? Is there some fairness criteria that we can attribute?
So I think you should clarify. So is the grand coalition the only possible stable coalition?
Actually, yes. Whenever we have super
Just
additivity,
wanted to point it out.
when we have super additivity, it means that the grand coalition is the only possible stable coalition, and this sort of relates to the question that you were asking just in there. No other coalition structure will be stable, because think about it, if you had some coalition structure, the grand coalition will always dominate over that, and that the sum rates they can get from it the sum rate will be greater, and then they can always distribute the extra rate that they got in a way that everybody gets more rate. So we asked this question about fair rate allocations. Can we pick one point out of these many points in a way that is fair to the cooperating users? And we treat this problem as a bargaining problem between the cooperating players. And we propose two fairness criteria, or two bargaining solutions. One is the Nash bargaining solution, which gives as a solution gains over the interference channel performance, which I'll explain in detail in a bit. And the second is a proportional fair solution. So the Nash bargaining solution is simply a way of picking one point out of these multitude of points in the core. It maximizes the product of the rate gains achieved by each link over its interference channel performance. What do we mean by that? Basically, we treat in the Nash bargaining solution, the utility of each cooperating link is treated as the difference between the utility it's achieving now, the rate it's getting now, and the rate it would get if it were alone, not cooperating with any user, which is the interference channel performance. And we maximize the product of this term across all users. And the point that we get out of this maximization, where RIs are allowed to be strictly greater than RIC, is the point picked by the Nash bargaining solution. So the Nash bargaining solution has some very good intuitive properties. It is Pareto optimal. It is symmetric, which means it doesn't depend upon how you label the cooperating players. So what falls out of this is a nice property that. So if you look at this, it's just simply intuitively looking at it. It's just sort of like an n-dimensional hyperboloid. So have this. You can think of it as an n-dimensional hyperboloid shrinking inwards, and the moment it touches this dominant face, or any point in this, you have a point which lies in the core. So basically, it suffices to search for the Nash bargaining solution only on the dominant face of the capacity region. Sorry.
Where does that curve come from?
This curve. So an intuitive geometric way of thinking about the Nash bargaining solution is basically I shift my origin of coordinates by RIC, where RIC is the interference channel performance of link I. Right. So here's my shifted origin, and this is simply just it's a product of R1 and R2 shift with this shifted origin shifted to R1 IC and R2 IC.
R1 IC and R2 IC are fixed numbers.
Yeah, they are fixed numbers.
No. So you only get a hyperboloid. Is that subject to the sum rate condition?
No.
No.
That's just a product.
You just get a family of curves.
I mean, you get a family of curves. You can think of. I'm just showing a geometric. Yeah. Is it clear? And we can think of after the Nash bargaining solution, we propose a proportional fair solution, which is defined in this manner. If RIPF is a proportional fair solution, RIPF is a proportional fair payoff assigned to player I, then any other payoff vector Ri would result in a negative fractional increase. Then RIPF is said to be a proportional fair solution. It has been shown that this condition is equivalent to simply maximizing the sum of the logs of Ri, which in our case just simplifies to maximizing the product of the Ri's. And again, you can think of it as a family of hyperboloids, except that now you don't need to shift the origin. So the proportional fair is sort of like a special case of the Nash bargaining solution, where the disagreement set, so to say, is now the origin itself instead of being the point denoted by the interference channel performance. We illustrate our results with three topologies, and we use not a fading model. We use a path loss model, which is with a path loss exponent set to 3. For each topology, we give the transferable utility allocations of Nash bargaining solution, the proportional fair solution, and we compare it with a simple non-transferable utility scheme, which is the equal rate splitting scheme I had mentioned earlier. So consider topology 1, where I have these 3 links. The triangles denote the transmitters and the circles denote the receivers. Link 1 and 2 are close by, and link 3 is far away. What do we see from this? don't worry about all those numbers. I'll explain what is important. NBS and PF, the Nash bargaining solution and proportional fair solution, lead to different allocations, but both are sum rate maximizing and yield stable grant correlations. The equal rate allocation, it's easy to see that players 1 and 2 don't have any incentive to stay in the grant coalition because they both can do better 1.4 against 1.3 if they broke away as coalition 1-2. So 1-2 breaks away from the grand coalition if I try to impose this equal rate non-transferable utility allocation scheme. Also, the equal rate tuple does not lie on the sum rate face of the CS, which implies that the proportional fair rate solution is not the equal rate tuple. Sorry.
Can you sort of explain that whole table?
Okay. So in this table,
Before you do what
Yeah.
she's asking, can you just storyboard the whole situation again? All right, so there's 6 people who want to communicate.
there's 3 people communicating with their receivers. No, sorry. So there's 1, 2, and 3.
But there's a sender and a receiver.
Sure.
All right.
Okay. For simplicity, I'll just use 1, 2, and 3.
All right. Okay, go on.
Okay. I'll just call the links 1, 2, and 3. 1 is the black line, 2 is the red line, and 3 is the blue line. The triangles are the transmitters, and the circles are the receivers.
Right.
The receivers can cooperate in the manner that I just described.
Transmitters don't cooperate whatsoever.
No.
Do they have any feedback whatsoever?
What do you mean, of course? No.
And
What
how will-
feedback?
How will the transmitters transmit at the correct rate if the receiver doesn't tell it, hey, okay, this
Feed.
is
Oh, okay. So not in a.
That
So
kind
they
of
have a
feedback.
kind of a.
So
So
a side channel.
someone has to tell them.
for
Someone has to tell
Drop
them
that right
that
now.
they've done
Okay.
this.
Sure.
All right.
Okay.
Now I'm
Yeah.
getting closer.
But as opposed to an active
Yeah,
feedback
yeah.
channel.
Assume there are more hidden wires everywhere.
Yeah.
Yes. So
Okay.
So-
fiber optics everywhere.
Yeah.
All right. Actually, I'm
No, or you
happy.
could just play
Okay.
the game ahead a bit of constant time.
So describing this table, here I list out different coalition structures, and here this column is for R1 rate, the rate for link 1, R2 and R3, and here's the sum rate. So in the first 2 rows we have these allocations corresponding to the Nash bargaining solution and the proportional fair solution, which both give the same sum rate because they both lie on the dominant face of the capacity region, but there are different allocations. And these 5 rows correspond to the non-transferable utility allocation strategy, which we use, the equal rate strategy. Only the grand coalition gives the same sum rate as the other 2 allocations. And I was focusing on this highlighted area. What I was trying to say is, if you look at the first row, which corresponds to the grand coalition, the rates received by user 1 and user 2 are not good enough in that if 1 and 2 broke away, they would both receive better rates, even though user 3 now falls to a low rate, but they don't care about that.
Okay.
So-
Nobody asked this question. I will ask. So, no. You already know what question I should. Which one is better, Nash bargaining or proportional?
So Nash bargaining and proportional fair are both, they are different fairness criteria. It's not easy to compare 2 different fairness criteria. But-
Bargaining is better
But I would say Nash bargaining has,
Let's see why he said that.
because the R2 and R3 are the same for like 3 decimal places or 2 decimal places. And the one guy, R3, is the same, right? And the other guy is, I guess the other guy, R2, gives up exactly what R1 gets, right? By some
second,
micro
third
amount.
decimal place.
So you could argue that, but on the other hand, right, they're closer equal to the Nash bargaining.
So one thing I can point out about the Nash bargaining is that
No, it's the other way around.
The other-
They're
it
closer
should
equal
should be.
proportional fair.
Just how it should
If you have a criteria to compare to criteria, why don't you maximize that criteria?
yeah.
That's the whole point of fairness, right? That was why I sort of.
So
I
maybe
was telling
proportional
him
fair is
yesterday.
a little better.
Huh? They're both Pareto efficient, right?
Yeah.
They're both Pareto
But,
efficient.
but Nash bargaining has sort of these other, and proportional fair is just a special case of Nash bargaining, where instead of bargaining over the interference channel rate, they're bargaining over 0 rate.
So Nash bargaining has this other intuitive appeal that the it relates to the interference channel performance. It maximizes the product of the gains over the interference channel performance. So in an intuitive way, I think Nash bargaining makes more sense. And also when Nash derived these.
Fair, those two guys have closer to equal rate.
Which is how it should be, right? Because you're maximizing your product given a constant sum.
So it's better, right? Because there's no reason one deserves the rate more than the other.
Yeah, it depends on the channel game.
No, but 1 and 2 are symmetric here.
I think
No, but drawing it matters.
Yeah.
One and two.
Look, no, the red guy has a receiver that is closer to the third interferer.
So this receiver
So therefore,
is closer to
those
this.
were, yeah. So I don't know. The red is 1 or 2 in your. Oh, it's
Two.
Okay.
Two.
Yeah, there you go.
So he does a little worse
Because he's
a little
closer to
receiver
the yeah.
It's sort of like a water filling in that sense, right? You get the best guy, the best deal. It's not fair.
No, it's fair. It's Nash bargaining fair.
It's Nash fire.
But I think it's subjective to compare two fairness criteria. I think it's a subjective thing to compare two fairness criteria, cross fairness criteria. But I personally like Nash bargaining.
But you better, because it's your thesis, right?
No, the thing is when Nash derived the Nash bargaining solution, he
That's what he got in question. No, not for Nash bargaining.
Nash equilibrium.
Oh, really? So that's
So Nash bargaining solution has some uniqueness property associated with it actually. So Nash.
You should say the other way, right? You first stated the properties and then this turned out to the.
True. So Nash stated 3 axioms, and he said some fairness criteria which meets these 3 axioms is a good fairness criteria, and then he showed that there exists a unique allocation which met those 3 criteria. So if there's a unique allocation which meets the NBS, then obviously the PF allocation is missing at least one of those 3 axioms. So that's why I like Nash bargaining.
okay. So since I delayed you, move on. I think you should move.
Oh, wait a minute.
Okay.
Yeah.
The same question.
And it's spaced out on right?
All right. So here's an even simpler topology. I've just placed 3 links symmetrically with respect to one another. The triangles are again the transmitters and the circles are receivers. And now we see that all 3 allocations are identical. The Nash bargaining, the proportional fair, and the equal rate allocation, they all coincide. They all lie on the dominant face, and there's not much to explain here. But when I squeeze link 1 and 2 closer to one another radially, and I keep link 3 where it was, and in fact I verified that the interference seen by the receivers of link 2 and link 1 has now gone up because their distances have decreased. So what happens is in this slightly skewed geometry of with respect to link 1 and link 2, the Nash bargaining and proportional fair lead to now different allocations. Let's compare it with the previous topology. So here they were getting like 0.9988, and here they're getting the Nash bargaining is giving you different lower results, 0.9868. The proportional fair and the equal rate lead to identical allocations because the equal rate point now happens to lie on the dominant face. And the grand coalition is sum rate maximizing and stable in all 3 cases. With that, I'll move on to the second line of work that we've done, and this relates to transmitter cooperation through ideal joint decoding. Let me describe our model. So now transmitters are allowed to cooperate. We have the same kind of links that we had before, and it is the transmitters who are now allowed to form coalitions, and I'll explain in a while how they cooperate. But first, let me say that all the receivers we assume now are cooperating. They're always cooperating. They don't form coalitions, and it's only the transmitters that form coalitions. We also assume that transmitters have ideal noise-free inter-user links, and cooperating transmitters do joint encoding by basically they appropriately structure their transmit covariance matrices. So we see that this type of cooperation turns the channel into a MIMO-MAC, a multiple input, multiple output, multiple access channel, where multiple input refers to the fact that a coalition of transmitters can be treated as one user with multiple antennas, although they have individual power constraints. That's important to remember. The multiple output refers to the fact that we have all the receivers cooperating, so it can be thought of as one receiver with multiple antennas. And multiple access channel because we can have multiple of these transmitter coalitions, which can be thought of several multiple users competing for the same resource. So it can be treated as a virtual MIMO. In fact, if all the transmitters were cooperating, it's basically like a MIMO, but each of the transmitters have individual power constraints. We are interested in which coalitions make optimal use of the available spectrum, that is, maximize the sum rate, and which coalitions are stable, that is, which coalitions belong to the core. So again, we model the problem as a coalitional game with transferable utility. And the first thing in any transferable, the first thing in any coalitional game is to try and define the value of a coalition, V of G. And we see that if we try to define V of G the same way we did before, that is, V of G equals the maximum sum rate between a coalition G of transmitters and the set of all receivers, it can be seen that V of G is no longer a characteristic value. It's not in characteristic function form, because it will depend upon what people outside G are doing. How are they encoding the signals? How are they structuring their transmit covariance matrices? So it's not right to move on this path. We'll have to adopt a different kind of theory, which unfortunately is very complicated. So what we did was we asked the question, how do we convert this to transferable utility?
Did you assume, I don't remember,
to characteristic
did you assume equal amount of transmitters as receivers now or not?
Yes.
It's always the interference channel. That means same number of transmitters, the same number of receivers. Each transmitter has its own receiver. It's all for the interference channel. Okay.
But
then we have these spectrum, whatever, the ways of making them co.
But to answer your question,
always keep interference channel, except
it's not the interference
it
channel.
never is when you
It never
actually
is.
do it.
No. And that's why I think we can state results for more than n equal to 2. Even for m equal to 2, you cannot say very much in an interference channel.
so yeah, it is the same, but I'll show in a while that even if I change the number of receivers to less than m or greater than m, then it makes a very small difference in the analysis. I'll show you. For example, I'll give an example later with just one receiver antenna, which is just a MAC, which is just a multiple access channel. Okay, so how do we convert this game to characteristic function form? We alter the value of V of G to reflect the maximum sum rate achievable by the coalition G, assuming worst case interference from G complement. So in essence, we are assuming that if a group of users attempts to break away from the grand coalition, the other users stop transmitting their own signal, and they transmit what is worst case interference for the set G. Basically, the users in G complement attempt to minimize the value of the breakaway coalition G. So this is a min-max problem because G is trying to maximize its sum rate and G complement is trying to minimize the same quantity. And in fact, this leads to a purely non-cooperative zero-sum two-player game between the entities G and G complement.
What do you say? G complement's trying to minimize its sum rate.
G's sum rate.
Alright.
It's like jamming.
Yes.
It's like
that's
jamming.
my point.
Yeah, we're just going to break away and jam the guys who are in the over.
Alright, but the value for G complement could be arbitrary.
Yeah. So this is for the purpose of defining the value of
Yeah,
G.
in fact, they are not rational. Right, you can argue that, saying that they don't care about what happens to their communication, but rather they want to.
Not rational, they're not selfish at that point.
Well, if I'm interested in getting a rate, I'm doing my communications to sort of screw somebody else without sort of caring what kind of rate I get.
So this is a rather harsh constraint. It's an extreme way of putting it. They may do it or they may not do it. But
Chris would be very happy. He couldn't be a sentiment. He wants to see your thesis
Oh,
and your
okay.
talk slides. Same thing my last night.
all right.
But as a resident paranoid person, I like that, so go on.
You're the resident paranoid person?
Well,
He's a
not
jamming
here,
guy.
I'm just
The jamming guy.
so.
See, Chris is always like, this is, life in the Bronx.
So this leads to a purely non-cooperative zero-sum game between the entities G and G complement. It's zero-sum because one is trying to maximize a quantity and the other is trying to minimize the same. And with this framework, we can define V of G now as a min-max of this function, where the min is controlled by the transmit signals of users in G complement, and the max is controlled by the users in G. And let me explain each of these symbols here. And before that, there is also this individual power constraint that we must not let go of. So QII here is less than or equal to PI, which is the individual power constraint of user I, and this extends to all users, whether they're in G or G complement. So in this formula, HG is a channel matrix for coalitions in G. HG complement is the same for users outside G. QG is the transmit covariance matrix of the coalition G. So it is essentially QG and QG complement, which is the transmit covariance matrix of users outside G, that the users in G and G complement are controlling to do whatever they want to do. So G wants to maximize its sum rate and G complement wants to minimize the same thing, and it is by controlling QG and QGC that they do this. QII is simply the diagonal elements of QG and QGC, which give us the transmit power constraint on user I. Digavi and Cover showed in 2001 that such a game with they call it a mutual information game between two entities, one who is attempting to maximize this mutual information and the other attempting to minimize the same thing, has a saddle point. And we use this property in proving that this game in fact is cohesive, which coupled with the probability of property of transferable utility implies again that the grand coalition is the only candidate for the core. Is there a question? I haven't shown it superadditive, actually, no. No. That was something I was working on, but I went back and checked, and I couldn't prove it superadditive. In fact, cohesiveness is sufficient to prove that the grand coalition is the only candidate in the core.
Right.
Superadditivity, as we were discussing earlier, is a stronger condition, but cohesiveness is sufficient to show that the only candidate in the core should be the grand coalition. But unfortunately, the only constraint we have in our problem setup for apportioning the rate between the transmitters is this, which basically says that the sum rate of all the users should be less than or equal to the value of the grand coalition, which isn't really a constraint. So we don't have any constraints on the sum rates of subsets of the set S. And we cannot conclusively show the existence of a non-empty core in the absence of any other constraints. In fact, we have counterexamples to show that the grand coalition cannot always be guaranteed to be stable. And let me show you one such example.
So even here, this is a feasibility problem.
Exactly, yeah. I was coming to that. So I take an example of an interference channel with 3 transmit-receive links. With this particular channel matrix, the rows in this matrix correspond to the 3 receivers, and the columns correspond to 3 transmitters. So the diagonal elements are the direct link gains between the transmitter I and receiver I. In this example,
Can you once more explain what you said just now? You said there are no constraints or something.
oh, okay. So yeah, sure. What I meant to say was, if you compare this problem broadly with the problem we had earlier in the receiver cooperation case, we had this nice structure provided to us by the capacity region that you could achieve by receiver cooperation. The way we have set up our problem doesn't lend us any such constraints. So a capacity region essentially gives us constraints on subsets, some of the rates of the subsets of S, right? We don't have such constraints here. We have only this constraint, which is some of the rates, some of the payoffs of all the users should be less than or equal to the value of the grand coalition, which isn't really a constraint. So in essence, you can operate anywhere as long as the sum of the rates you allocate to the sum of the payoffs you allocate to all the users is less than or equal to V of S.
Why are there no constraints? I didn't get that.
It's a cooperative map, right?
Okay.
So
All the transmitters are.
So in the beginning, I said that I have perfect inter-user links between transmitters. Okay, so if all the users act collectively, all the transmitters, and they achieve a certain sum rate, they can distribute that rate anyway. They can give all the rate to one user and zeros to the others. So we don't have those constraints. We don't have any constraints stopping.
Okay. So I mean,
It's like a MIMO.
you don't have those boundaries. I mean,
Yeah, you don't have those boundaries. Think of allocating.
When you talk about the capacity
can't
of
you
the
say
MIMO
like
channel,
zeros? I mean, zeros as constraints. I mean that rate
those are the
I mean, obviously you wouldn't go to 0 because each user will have a certain v of I. If you give him 0, his v of I will be greater than that, his own value.
Without the constraints, what is the problem? I mean,
Which constraints?
if you don't have constraints, then what is the problem?
No, you
The
have
problem
You
is,
can't show those two things. That's what he's saying. That implies what he wrote. See, the whole point is this, right? He said that the game is cohesive. That means one thing is obvious. The only candidate for his score is the grand coalition. So you just have to check if the grand coalition is stable or not. And he says just because he doesn't have enough constraints, like he cannot use the same tricks he used in the receiver cooperation case to show stability. And this is an open problem, right? I mean,
so we haven't, I've tried to work on an analytic proof to show
in
that
fact,
the game is.
Then he said, let's try to see if we can find counter examples.
Okay, then we count it.
Yeah.
I mean, you can
So,
pose analysis also as well.
to answer your question, what is the problem? The problem is, what is the optimal coalition structures? Cohesiveness, which we derived by the saddle point property, tells us that the optimal coalition structure is the grand coalition, and optimal meaning that the sum rate is maximized. And the second question that we are posing throughout our work is there stability? Oh yeah, I don't have an analytic proof for stability. So I tried working on an analytic proof. I wasn't able to find one. So what I did was I went and looked for counterexamples, and we did find counterexamples. And I'll show you how we went about doing that.
So what's open about this? It sounds like you found, in the counterexample, you found though the theorem you're looking for is decidedly not true.
Yes,
So
yeah.
You're right. Nothing open. He just said it's not.
I'm just saying
You
I
can't
wasn't.
guarantee stability.
Yeah.
That's all he's saying. But are there some channel gains for which it's stable? Sure. No.
So what's the problem here? Is the problem that conceptually that the remaining people aren't necessarily capable of punishing the defectors? Is that the
Yeah.
gist of the issue with stability?
The issue is with when G wants to break away, G complement can punish them by minimizing their sum rate. So if they weren't able to do that to a good enough extent, then G would still break away. So what I'm showing by these examples is that this does happen, that G sometimes breaks away, and you cannot guarantee.
But what Roy is asking is sort of prompting some very interesting new ideas to pursue. Not you, somebody else, I think. Essentially, you can put rate. When you break away and try to do something, you can put some constraints on how they should care about some minimum rate for themselves before they go around screwing up the coalition.
Oh,
That might give you a handle on this problem. Actually, that's very nice.
Meaning people won't do themselves the maximum injury, devote themselves.
That'll allow you to put some constraints into the problem that might.
Actually, I have a comment on that.
Yeah.
So here we are assuming that the G complement users, they forget about their own benefit
I know.
and they jam you.
Right.
So now if they didn't do the worst case jamming, right, then the users in G would actually do better. So they would have a greater incentive to deviate, which is sort of supporting this result. You see?
So it's really, so you're saying it is the inability to punish with great
It is,
effect.
yeah. So actually what we've shown is even in this extreme assumption that users in G complement will devote all their transmit power to jam users in G, we've shown that users in G do defect sometimes. That is, we do have empty cores. So if they were not doing the worst case jamming, the V of G, so to say, would be even higher.
So can we go back sort of to the physical model to say, understand why defecting is good? So there's, just refresh my memory. The transmitters are cooperating, and there's one big powerful receiver that collects all the signals or not?
Basically, it's one receiver for each transmitter, but we are assuming here that all the receivers are jointly decoding. So it's like one receiver with multiple antennas.
So when this first problem, when we started looking at it, right? So my initial intuition was that if everybody cooperated with everybody else, you essentially have the virtual minor channel, right? Of course, with individual power constraints, like what Kunal has. And I always used to tell him, like, it seems so obvious this should be stable. Why would you not want to do that all the time? It turns out you don't.
Another way, if you can visualize this looking geometrically and see that
Jamming.
you have
That's
this
because the
rate
jamming
region,
concept.
You have a total
Because the jamming
cooperative
concept.
region, and then you have these
No.
other regions.
No, that's not it. It's just because of the jamming concept.
But my
The
point
moment
is-
you say that people are willing to go out and just screw somebody else and not care about what performance they're getting, right? Then basically it says that people will go out and do it.
No, but he's making a
Similar to our message.
oh.
That's something to look at. Yeah, but here these antennas are screwing up the other one. That's sort of the min-max, right? Yeah, yeah. See, I mean, go and show your value function, right, that you finally defined.
Oh. So
See, we had to make this definition. Otherwise, the game is not characteristic form to start with. Right.
so basically in this function, basically you have these parameters qg, which are controlled by the users in G, but qg complement and qg complement, they both appear in the numerator and denominator. Essentially, the property of this function is that it's convex in the it's convex in the minimizing variable, which is
Right.
qg complement, and it's concave in the other one. So
Right. That's fine. So and then he has a saddle point, which Pigavi and Kobe were shown and all that. But the important thing is look on the left side. This is just talking about the value of G. So the question you can ask is, what is the value of G complement? There is no value. Maybe not even looking at that.
Sure.
We're just looking at essentially a jamming game where people are given the option of going out and jamming. And will they
That's
do
true.
that? That's sort of the premise now.
Suhas, when you're comparing like the say grand coalition with another coalition, when you're showing that it's not stable, right? Then what are the rates, like how are the rates apportioned in the grand coalition? Like you have to compare the rates of each individual.
No.
yeah, so
Let's
flexibly.
go what you did. I think you should go back to the slide you were talking.
Okay, so I'm ready to see the slide you were.
Show
You're
the
going to
example.
show us your example.
Example? Okay.
Yeah.
Okay, so essentially you're asking me how I got this thing. I'll
What
show
do you
you.
compare? You
Yeah,
have
I
to
just-
fix some proportion, right? Like
Okay.
Tell you once.
So here's the channel matrix.
Maybe it'll be better in this example.
Here's a certain channel matrix, which is for an interference channel with 3 transmitter and receive links. Each row corresponds to a receiver, and each column corresponds to a transmitter, and the diagonal entries are for the direct transmitter to a receiver link. Yeah. So all the direct channels are strongest except for user 1. User 3 has very little interference from user 2 and user 1. This is a direct channel of user 3. So these two are very small. User 2 has significant interference from user 3. User 2 is this is the direct channel of user 2, has significant interference from user 3, and user 1 has significant interference from user 2, in fact more than its own direct channel. So recall that the existence of a non-empty core is equivalent to showing the feasibility of a linear program, which is what I stated when I showed that toy example. So that's the principle we use here to check for whether the core is non-empty or not. We basically check the feasibility of the linear program that springs from this example. Okay. So I write all those linear inequality constraints. In this case, there are 3 users, so there are 15 inequality constraints and one equality. And it turns out that for this example, the linear program is infeasible, which means that the core is empty.
Yeah,
And
but this is a proof by MATLAB, though.
this is a proof by
Okay,
MATLAB.
but
So it's not a proof; it's a counterexample.
What's going on in this example? So
What's
I'm
going on
wondering-
is-
I mean, I see the one
Yeah.
physical
So
here.
here's the thing,
Is
Suhas.
that
Can you just go to the board? I
Yeah.
asked him to draw this picture for this.
Yeah,
right?
please.
I told him to draw the transmitters and receivers, and he said, I'm not sure what to draw. So
Okay,
if
so-
you draw it, then I think it will help us.
Transmitter 2 is right near receiver 1.
I think link 2 is the longest. We start with that. Link 2 is the longest link because
So
link length, keep them as the
you
direct
can
channel.
fix the link.
I don't know if I can draw this to scale or not.
Does it matter?
Keep a bold or
I don't understand
Yeah.
why it matters, like which one of the receivers you have a really good gain to, because the coding is always using all 3.
It doesn't matter.
Yeah.
It doesn't matter. I mean, I'm not saying that this was infeasible because of a certain structure in the matrix.
Well,
I'm not claiming that.
obviously infeasible because of that, because the matrix defined everything.
Sure, but I'm not pointing out what was
We couldn't-
what was
yeah, it doesn't
responsible
have
for that. I don't know.
a- Doesn't
Well,
have a
how
sense.
did you come up with this matrix then? If
No, but
you-
maybe
I'll-
there was some intuition behind using some links as much worse than others.
But if 3
That
points
was
don't
an
form a
idea.
triangle with this, then there's no point in it.
Yeah.
Do a lot of random deployments and
Yeah, you're right.
So the way I went
Hold on,
about
let him talk.
yeah.
the way I went about doing it was, I threw 3 links and 3 receivers, and I did random channel initializations. And for each such matrix, each 3x3 matrix, I ran a feasibility check on the linear program that resulted from it. And and I did this in MATLAB.
You know
And
what?
if
Do me a favor. Show me the 5-user example. Right? That might be simpler to understand.
You mean the math?
No, just watch.
so,
Okay, let's do
Oh,
this.
sorry.
This one I think is.
yeah, this is more feasible, I think. So this is just one receiver. So it's a cooperative MAC, which there are 5 users, and following the same cooperative strategy, there's only one receiver now. Okay, so here you can see that the channel link, the link gains are quite comparable. They're not very different from one another.
Except for that one, user 3 is like 2 orders of magnitude below the other guy.
Right, I take that back. So yeah, this one, yeah,
Yeah.
sure. And I did the exact same thing with this. So there's one receiver and 5 transmitters, and it results in actually more linear inequality constraints than the 3-user case. And basically, the idea was to check for feasibility of the linear program. And if it was feasible, if it was infeasible, it clearly shows that this linear program doesn't. There is no core. The core is empty. If the core is empty, it means that the grand coalition is not stable, and that means that there is no stable coalition structure at all.
But what is okay? So okay, you have a suppose you have a grand coalition, all 5 people, you know. So in that case, there is some partitioning of the rates that they all get.
You know, can you go show that?
Right. So
Alpha
who's
is-
gonna defect?
Go to the slide on alpha.
Alpha?
Just show that. Go back to that slide where you had alpha equals 2 over 3.
Oh, that.
Just show that. So that we're all clear sort of on exactly what these constraints are. Okay.
Okay. So basically, I did this sort of thing for each of those examples, right? So for there to be
And the
at least
difference
one
here is
point.
that those things are not 0 when they are by themselves. They
Sure,
get
yeah.
whatever interference channel or whatever
Yeah.
performance they get.
Yeah. I mean, this is a very simple example, but here now I have transmitter cooperation, and just like each of these quantities, I can think of, just like each of these inequality constraints, I can think of an inequality constraint in that example, and the idea is to show that this entire set of inequality constraints has at least one feasible solution.
So I know, Roy, I sort of don't see it so much as who wants to defect. I somehow see it as like in that 5-user example, there was one guy who was really bad. I think the 4 people gang. See, he did not.
I did not show who defects. Yeah.
He did not show anything like that. What he did was he looked at the value function for all possible. If there are 5, how many possibilities are there? 15. How many preference sets are there? Whatever.
But I mean,
With
look,
3, there are
if you have
15.
this example, like if he says the grand coalition.
Yeah. So the 4 people kicked the one guy out because they didn't want to give him any rate, and whatever jamming he does, that they still are better.
I mean, it's, okay, that's
exactly what the answer
That's
is.
what I was looking for, but I
Yeah.
don't understand why he isn't just saying that.
Right.
I think
What?
that is what I was trying to get him to sort of illustrate.
So I haven't.
Do you agree with him? Because you seem.
Go to the 5-user.
I was
This one is too
expecting you to
complicated for me
say
to
that.
understand. This 5-user example, right?
Yeah.
Here is what I told Roy.
Yeah.
I told him here the grand coalition not stable
Yeah.
because the one guy who has a really bad chance. In fact, that is how I asked him to start. I said, do an example where one guy is like a really weak link. We don't even care about him if he's there or not, right? So why would anybody want to include him in a coalition?
I guess that what I can't understand is by including him, what penalty do they suffer?
They have to give him some rate that is at least as good as his interference channel rate.
Okay, okay.
That means
Uh,
that the sum rate is not dramatically.
No. The penalty they suffer is that out of the sum rate they get, they have to give him a share that is at least better than his singleton value.
So wait, hang on.
Okay? So then I'm saying if he's such a lousy link, who
Lousy means
cares?
he's lousy to you, he can't hurt
He's
you.
lousy, yeah, he can't hurt you. So then he's saying like, let him do whatever he wants.
So when-
kick him out.
when these-
That's what happened.
When all 5 people are in a grand coalition, they have to distribute the sum rate in such a way that not only is each individual user happy,
Yeah.
Each
that's
subset is
medium
also
program.
happy.
That's what I asked you to show the medium program.
I understand. that.
each
Yeah.
each subset is
That's
also
what
happy.
it is. It's not like
So the resources they give him in terms of of channel uses or
Right.
something, right? For him to get it is
Yeah.
more than if they just ignore him.
Right.
and
So
did the
this
other
is
one.
exactly what I told him. I said, right, put one guy who's really weak, and let's test those cases. And it turned out
It turned out actually those, like I did random channel initializations, right? So the ones I got stuck up with, that is the ones I saw were infeasible, turned out to be the ones in which one has an extreme channel compared to the others.
So can you take him like what population is?
Hold on, there are 5 people, right? So if all 5 are there, each one should be given a rate, even the weakest guy should be given a rate that is better than him being by himself. You should remember the linear program, he had R1 greater than something, R2 greater than something, and all this sums. So then it is a really lousy channel in the sense that he's not interfering with you much. People say, let him go out and jam us, we don't care. We are still doing better by kicking him out. That's what it is.
Yeah, I've noticed because like the boundary of the region is like
No,
Yeah, but it's so small, the difference going from just 4
it would be interesting to see what
So-
the rates are that they get.
No.
You should be able to compute these values. For
The-
the constraints that you put, you should be able to see what they are.
Yeah, but I don't have them in the
I know you
presentation.
don't have them.
Yeah.
I think that's something. Yeah.
So let me take a simple example too. So if I had three users and
In that example, right?
yeah,
Like that configuration of 4 and 1 seems like that should be stable.
Yeah, I mean, he's not
I don't-
proving that there is no.
No. So here's
So,
the thing. So that's what I'm going to show you. So what he said is that essentially the grand coalition is not stable.
Yeah,
That's all.
yeah.
So when he said no stable coalition it is, I'm not sure what that means.
I'll tell you what that means. So
For 3 user case, was that true? I mean, that no.
yeah, so we've shown by this that the grand coalition is not stable. Now fall back on the property of cohesiveness. What does that say? If you had any other coalition structure, any other partitioning, not the grand coalition, any other partitioning, then the grand coalition will always dominate over it because it would get a greater sum rate than what they're getting right now, and the extra rate that they get, they can arbitrarily distribute it to make everybody happy. So cohesiveness itself has already ruled out all other coalition structures. So it's only the grand coalition that has any possibility of being stable, and we've shown that the grand coalition is not stable, so there's no stable coalition structure.
So actually, the thing is this, right? I don't think he has run a game and see what happens to the dynamics. Should probably do that to see. When you say they're not stable, that means you should be oscillating between various groups of people, right?
You'll keep oscillating.
Yeah.
There's no
So
equilibrium.
what happens? Can you find out what happens in this one? Like
This-
1, 2, 4, 5.
Yeah.
Well, why doesn't it just stay there?
Maybe there are issues amongst them too. See, one of them is 10 to the minus 3, the other is 10 to the minus 1.
Well, why don't we simplify this? Do you think
Yeah.
this would work out if you made 1, 2, 4, and 5 all be identical, and user 3 be the low bound?
Oh, in that
I don't know.
example, I bet you the grand coalition is stable.
There are examples in which it will be stable.
Is a property that's proved directly from the saddle point property of that min-max optimization. Okay. So the moment you have a cohesive game, all right, the grand coalition is the only candidate for your core. Okay. So therefore, I bet you. You know what? We should just revisit this example
Yeah.
and do exactly what he said with
So you're saying
make everybody equal except
one of
guy.
them.
You might also write down, explain what happens in the saddle point, because you only have a one-dimensional signaling.
Yeah.
Right? All your matrices all
Yeah.
filled up,
So
and it ought to make it really obvious.
yeah, so I can tell you what happens in the saddle point for this case when you have only one receiver. All the transmitters choose to basically maximize all the off-diagonal elements in their transmit covariance matrix. Basically, the correlation between all the transmitters is the maximum possible in the jamming coalition as well as in the defecting coalition. That's the saddle point. It's a very simple saddle point for the case of one receiver. In fact, I ran this for greater than 5 receivers, and it turns out that if I went up to 10 transmitters in one receiver, and this is like an empirical thing I saw. I haven't proved it or anything, but as I increased the number of transmitters, I saw more and more examples where very similar channel gains were resulting in empty cores.
It's not clear why, in this example, that more transmitters makes any difference.
Yeah, I'm not sure about
Or
that.
it's also not clear to me. Like Narayan has some insight that he thinks, if 1, 2, 4, and 5 have equal gains,
Yeah.
right? He thinks then the grand coalition becomes stable again.
I don't know. I'll have to check that.
I mean, you work with a lot more than I do. I don't see it based on what little I understood.
The reason that it doesn't.
I don't see that.
Why
Yeah.
don't you work on the variations of this and find out what?
Okay.
Yeah, I think you should just stick to the simple Mac example.
Okay.
Right? And,
Already confused the heck out of this.
So that brings me to the third and final part of my work, which is receiver cooperation through multi-user detection in a multiple access channel. So let me explain what I mean by that. So we consider linear multi-user detectors for receiver coalitions. Basically, if I have several transmitters and I consider this in the context of a MAC, I could form a multi-user detector on a per coalition basis. Basically, I have to explain this picture, I have several transmitters and one receiver, and I pass the received signal through a bank of matched filters. So if I had n users, I have n matched signals coming out of it, and I could bunch, say, a group of signals G and form a multi-user detector for only those people in G. Okay, and we model the SINR achieved by a user in a coalition as its payoff, not the rate. This time we use SINR as a payoff. This is a non-transferable utility game because in a linear multi-user detector, the SINR achieved depends upon the linear transformation that I use for the multi-user detector, and the SINR cannot be exchanged in a fluid manner. So it's a non-transferable utility game. Users within a coalition benefit from the interference suppression offered by their multi-user detector. The received model is as follows. Like I said, there's one received signal which depends upon the powers of all the users, which we assume the same here, the channels, the bit, and the signature sequence, and a noise term. And the vector of matched signals can be written in this form: y equals RAB plus n, where R is the correlation matrix between the signature sequences of the users. A is just the received amplitudes, and B is a vector containing the bits, and n is a vector containing the noise. The received signal vector for a coalition G can be expanded as follows, where this term corresponds to the received signals of users in G, and I've separated out a term which corresponds to signals from users who are not in G, and there is a noise term. So basically, we take the vector of signals corresponding to users in G and we multiply it by this linear transformation, and depending upon what what receiver we're using, we can plug in different things for LG. We consider two receivers here, the decorrelating detector and the MMSC detector. For the specific case of the decorrelating detector, the SINR of user I in a group G can be written by this big expression here due to Lee and Ephremides, and we assume here that all users in the system have identical cross correlations denoted by rho. One thing that comes out of this game is the decorrelating detector MAC game has a stable grand correlation, and the grand correlation is also sum rate maximizing in the high SNR regime. And that readily follows from this relation. If you look at the SINR of user I in coalition G, and you let sigma square tend to 0, that is the high SNR regime, the SINR of user I would always be greater if it was part of the grand coalition than if it were part of any other coalition G. So every user would want to be part of the grand coalition. And that immediately implies in a non-transferable utility game that the grand coalition would be stable, and also sum rate maximizing, because we assume that there is a non-decreasing monotonic mapping between SINR and rate. In general, however, there is no guarantee that the grand coalition of users should form. We've only said this for the high SNR regime, and there's no guarantee that the stable coalition structure should be the one that maximizes sum rate. And to illustrate these points, we use this simple mapping of rate equals log of 1 plus SINR. This picture shows on the left hand side the stable coalition structures in an example with 3 users. When users 1 and 2 have their received SNRs varied, and user 3 has its received SNR fixed at 27 dB, and one can see that the stable coalition structures keep changing. Of course, in the high SNR regime, which corresponds to the top right hand corner, the grand coalition is stable. On the right hand side, I have the equivalent picture for the sum rate maximizing coalition structure, utilizing the rate equals log of 1 plus SINR mapping. And again, you can see that different coalition structures are sum rate maximizing. It's not always the grand coalition, but in the high SNR regime, which corresponds to the top right hand corner, it is the grand coalition. When we use the MMSE receiver for cooperation, we find that the grand coalition is always stable and sum rate maximizing. This follows from the fact that minimizing the mean square error is equivalent to maximizing the SINR. Hence, every user wishes to be part of the grand coalition. Since every user wants to be part of the grand coalition, the grand coalition is stable. And we also assume that the SINR to rate mapping is monotonically non-decreasing. Hence, maximization of every user's SINR corresponds to maximum sum rate. So the grand coalition is always stable and sum rate maximizing for the MMSE receiver. This brings me to the end of my presentation. We have seen that cooperation in wireless networks can be studied under the framework of coalitional game theory. The grand coalition is often optimal for maximizing the utilization of shared spectrum. And when we say utilization, we've considered it by maximizing sum rate. When cooperation is cohesive, the grand coalition is the only candidate for stable cooperation. Ideal receiver cooperation is guaranteed to have a non-empty core, and when in fact the core is non-unique, bargaining theory can be used to pick a fair point. A non-empty core cannot in general be guaranteed for transmitter cooperation. And finally, when there are costs to cooperation, cohesiveness cannot be guaranteed, and disjoint stable coalitions may result. Example, noise enhancement, like we saw just now in a decorrelating receiver. And finally, some future directions of interest. We would like to be able to have distributed means for coalition formation and distributed means for bargaining. Another interesting question is how much cooperation is needed. Can we quantify cooperation by some means and ask the question, how much cooperation is needed to guarantee a non-empty core? And finally, there's this particular problem that we're interested in working on, which is transmitter cooperation through user cooperation diversity, as proposed by Sendonaris, Urquip, and Azhang in their much quoted user cooperation diversity paper. We have some preliminary analysis on this model, and we conjecture that this type of cooperation may result in a guaranteed non-empty core. With that, I come to the end of my presentation. Any questions?